Welcome to this Edinburgh Instruments virtual demonstration. In this instalment, we will discuss how to configure a Raman microscope system in Ramical to optimise the quality of a spectrum. Here, we will discuss exactly what constitutes a high-quality Raman spectrum and show how each component within a Raman microscope can be used to make the most of what is a highly information-rich technique. Before discussing the methods for optimising spectral quality, we should consider what actually makes a good Raman spectrum. The appropriate threshold for a good spectrum is dependent on the research application. However, there are key parameters that must always be considered. The main three are spectral resolution, sensitivity, and range. Resolution indicates a system's ability to resolve different features in the electromagnetic spectrum. If two features of interest are close together in a spectrum, then a high spectral resolution is needed to identify them as separate. If the resolution is not sufficiently high, separate features can be wrongly assigned as the same. Sensitivity is the magnitude of the signal detected in a system and is characterised by the signal-to-noise ratio. If sensitivity is high, spectra appear smooth and all bands from the sample are visible. If sensitivity is low, spectra appear noisy and expected peaks may not be visible. Longer acquisition times are then needed to reveal these peaks. The spectral range is the amount of the electromagnetic spectrum a system can measure. Large spectral ranges are not commonly required. However, a more extensive range can be advantageous when a user wishes to detect high wave number Raman peaks alongside the fingerprint region, or even configure a system for photoluminescence measurements. These three parameters are always in balance, meaning that favouring one will likely be at the expense of another. For example, if a user wishes to optimise resolution, then sensitivity and range could be compromised. It is essential to consider this balance when optimising spectral measurements for your research application. Another factor that must always be considered is fluorescence, a competing phenomenon in many samples that can obscure valuable Raman information by elevating spectral background levels. If the sample is fluorescent, mitigating it through the system's configuration is advisable, although the methods used could also affect any of the other three previously discussed parameters. Now that we have a better understanding of what constitutes a good Raman spectrum, let's see how each computer controllable component can be configured in Ramical to optimise a measurement based on the different spectral quality parameters. In the spectral measurement window in Ramical, each component within the system that can be selected and changed is presented in the panel on the left-hand side. These include the laser, the diffraction grating, the confocal pinhole, and the entrance slit to the spectrograph. The acquisition time of the measurement can be entered in the box at the bottom of the panel. Raman excitation sources are typically monochromatic continuous wave lasers, and the laser's wavelength significantly affects resolution, sensitivity, range, and whether fluorescence is observed. The RM5 can fit up to 3 internal lasers, and the RMS1000 can fit up to 5 internally plus externally coupled lasers. These are accessible via the drop-down menu at the top of the panel. Let's start with how the laser affects resolution and range. Since the relationship between the wave number Raman shift unit and wavelength is reciprocal, the resolution of spectra recorded with higher wavelength lasers is better than with lower wavelength lasers. The range achievable with each laser is linked to the maximum detectable wavelength, which is governed by both the detector and the grating. Lower wavelength lasers provide a higher spectral range because they are further removed from this limit. What about sensitivity? The effect of the laser on this parameter can be summed up in the equation that defines Raman scattering intensity. The magnitude of the Raman intensity is directly proportional to the laser power and has an inverse fourth power dependency on laser wavelength. This means firstly that increasing the laser power will increase the intensity of the Raman bands in a spectrum. Power is controlled in Ramical using a drop-down menu that activates a neutral density filter in the laser path, with the 100% option meaning complete transmission of the laser. The laser power should first be set to low power and iteratively increase when testing new samples, because high laser power can lead to sample burning. The inverse fourth power dependency of wavelength means that lower wavelength lasers will produce more Raman scattering than longer ones. Therefore, the sensitivity of the measurement will be better. However, this rule only applies when the effect being measured is conventional Raman scattering, and is likely to break down when resonance or surface-enhanced Raman scattering is measured. In these instances, the optimum laser wavelength for sensitivity is sample dependent. Changing the laser wavelength is also the primary method for preventing the emergence of fluorescence backgrounds in Raman spectra. Most samples that fluoresce absorb and emit in the visible region. Therefore, lasers in the near-infrared and even in the UV can be used to avoid the electronic transitions of a wide range of fluorophores. This is also heavily sample dependent, however. The next component that can be selected in Ramical is the diffraction grating. Each spectrograph in the Edinburgh Instruments Raman systems can fit up to 5 software controllable diffraction gratings. But how do they affect spectral acquisition? Gratings are characterised by a metric called groove density, which is quoted in units of grooves per millimetre. Gratings with a higher groove density are better at dispersing light into its constituent wavelengths, producing higher resolution Raman spectra. However, low groove density gratings provide higher sensitivity and range because the low degree of dispersion means that a larger wavelength range hits the detector and more photons hit each pixel in the detector array. It is possible to acquire high-range, high-resolution spectra using the extended scan feature in Ramical. To achieve this, the diffraction grating is rotated between high-resolution spectral snapshots, which are stitched together to form a high-resolution spectrum over a large range. The confocal pinhole is most useful when the sample under investigation has multiple different layers. By closing the pinhole, Raman scatter from layers out with the focal plane is diminished in proportion to the layer in the focal plane. It's also useful for eliminating fluorescence from the surrounding sample volume. The consequence of closing the pinhole, however, is that the magnitude of the Raman intensity collected is reduced, thereby affecting spectral sensitivity. Higher acquisition times are commonly required to achieve a better signal-to-noise ratio. The final component that will be discussed in this tutorial is the slit, which is the aperture that controls light input into the spectrograph. A wide slit allows more light to enter the spectrograph, which increases sensitivity. Reducing the slit size decreases sensitivity but improves spectral resolution. Let's sum up what we've learned. Spectral quality is dictated by spectral resolution, sensitivity, range, and a lack of fluorescence backgrounds. Each of these parameters can be controlled using the configuration of the microscope. To improve resolution, use higher wavelength lasers, higher groove density diffraction gratings, and a smaller slit width. To enhance sensitivity, use lower wavelength lasers, lower groove density diffraction gratings, and larger slit and confocal pinhole sizes. To achieve the best range, use low wavelength lasers and low groove density diffraction gratings, or use the extended scan feature in Ramical with higher groove density gratings. To ensure the spectrum does not contain unwanted fluorescence, carefully select the laser wavelength to avoid the absorption window within the sample, or close the confocal pinhole to reduce emissions from out with the focal volume. Finally, if the research application does not demand that one of these parameters is enhanced at the expense of others, high-quality spectra should have a balance between sharp peaks with high resolution, a high signal-to-noise ratio, a large spectral range, and minimal sample backgrounds. We hope that you have found this tutorial useful. Thank you for watching, and please keep an eye out for more Raman spectroscopy videos soon.